In order to prove the Whitney embedding theorem, there are two fundamental tools that we are going to use. The first one was introduced in last lecture, and it is the Sard theorem. And the second one is partitions of unity. This is a very useful ingredient in differential topology because it allows to globalize some local results. So we need partitions of unity in order to globalize some local properties. There are partitions of unity for CR manifolds where R is between 1 and infinity, but we don't have partitions of unity for real analytic manifolds. As a consequence, the study of a real analytic case uses different techniques. Let's give the definition of a partition of unity. Consider first an open cover of a differentiable manifold M. In the unique condition that these open sets UI satisfy is that M is the union of UI for the elements of the family. That's what being a cover means. And a CR partition of unity subordinated to this open cover is a family of CR maps such that the following conditions are satisfied. The first one is that the image of these maps is contained in the closed interval 0, 1. And moreover, we are going to require that the support that is defined here to the right is the closure of the set of points in which the function is different than 0 is contained in UI for every I, for every index. Moreover, we are going to require that the family of supports is locally finite. What does it mean? We say that a family of sets is locally finite if given any point, there exists a neighborhood U of this point that intersects just finitely many members of the family. Why is that interesting? Because when we consider this sum over here, we don't want actually to consider limits. We need that for every x, and indeed in a neighborhood of every point x, we need that the number of functions that are non-vanishing in a small neighborhood of x is finite. Because in that way, this sum over here becomes a finite sum. And so that's the point where the locally finite condition appears. Okay? An equivalent definition for being locally finite is that any compact set intersects finitely many sets of the family. Okay? So the theorem of partitions of unity says that if we have a manifold M, that it is Hausdorff and paracompact, and we consider an open cover of such a manifold, then there exists a CR partition of unity, M is a CR manifold, subordinated to that cover. Let's remind ourselves that subordinated here is that this support is contained in UI, okay? That's the connection between the family of functions and the sets of the open cover. Okay, so we're going to discuss a little bit these two properties, being Hausdorff and paracompact. A topological space is Hausdorff if given any pair of points in the space, any pair of different points, there exist disjoint neighborhoods U of Y and B of C. Okay? And let's point out that our definition of manifold does not exclude non-Hausdorff manifolds. For instance, we could consider the line with a double point. What is that? We get here R minus the origin, and we have the line, we remove the origin, and we replace this origin with 2 points that we can call 0 plus and 0 minus, right? And there we defined 2 local charts. The first one is defined in R star union 0 plus to R, and sends x to x if x is different than 0, and 0 plus to 0. And we can do essentially the same by replacing here plus with minus. Okay? There we have 2 local charts for this topological space that is obtained by considering the real line minus the origin and O plus and O minus. And what happens is that the change of coordinates, is defined in R star, and it's just the identity map. Indeed, we could use these charts to give a topology to this space. And clearly, this space is not Hausdorff, because if we want to consider now a neighborhood of 0 plus in this line with a double point, the way to do it is using this local chart, and it's going to be the preimage of a neighborhood of 0. So in particular, a neighborhood of the point 0 plus is going to contain regular points. It's going just to be a neighborhood of 0 in which we are replacing 0 with 0 plus. And the same thing happens with 0 minus. And so it is clear that any neighborhood of 0 plus intersects any neighborhood of 0 minus. So this manifold is not Hausdorff, right? But something that it is interesting is that a non-Hausdorff manifold does not satisfy the partitions of unity theorem. And why is that? If the manifold is non-Hausdorff, okay, there exist 2 points, indeed 2 different points, such that any neighborhood of Y intersects any neighborhood of C, okay? So that every neighborhood, if U is a neighborhood of Y, and W is a neighborhood of C, then the intersection of U and W is non-empty, all right? But now we are going to consider an open cover of M that contains just 2 open sets, okay? And it's going to be, the first open set is going to be M minus Y, and the second one is going to be M minus C. Those 2 sets are open sets, and obviously the union of these 2 open sets is M, right? Okay, so here we are. And now let's assume that the theorem of partitions of unity is satisfied. Let's try to obtain a contradiction. So if the theorem is satisfied, then there are two differentiable functions, theta and theta prime, defined in M, whose values are in 0, 1, such that the support of theta is contained in the complementary of y in M. The support of theta prime is contained in the complementary of the set whose all unique element C, and besides that, the sum of theta and theta prime is equal to 1. Right? Let's see if this is possible. But the issue is that if the support of theta is contained in M minus y, that means in particular that theta is 0 in a neighborhood of y. There exists u neighborhood of y such that theta restricted to u is equal to 0. And in the same way, we can find, let's say, so what we just proved is that there exists u neighborhood of y such that the restriction of theta to u is equal to 0. Okay, but now we can actually make an analogous argument with C. And because of that, there exists u prime neighborhood of C such that theta prime now restricted to u prime is equal to 0, right? But what we have is that theta plus theta prime restricted to u intersection u prime is equal to 0, right? Because both functions are 0. And since theta plus theta prime is equal 1, what we get is that u intersection u prime has to be the empty set, which is not true because we know that every neighborhood of u intersects every neighborhood of C. So this intersection over here is indeed non-empty. And so in this way, we obtain a contradiction. So recapping, we considered a non-Hausdorff manifold and we assume that the theorem of partitions of unity holds for any open cover. And we obtain a contradiction. So if a manifold satisfies the partitions of unity theorem, necessarily it is a Hausdorff manifold. Okay, so this condition, it's actually a necessary condition. Let us consider now the other condition that appears in the partitions of unity theorem, paracompactness. Let's give the definition of paracompactness. Consider an open cover of a differentiable manifold M. A refinement of such an open cover is another open cover such that every element of the new open cover is contained in an element of the old open cover. Okay? And now let's give the definition of paracompact. a topological space is paracompact if every open cover has a locally finite refinement. Okay, that is the definition. If M satisfies the conclusion of the partitions of unity theorem, then it is paracompact. Okay, and why is that? As we already said, a topological space is paracompact if every open cover has a locally finite refinement. But if M satisfies the conclusion of the partitions of unity theorem, then we can build this locally finite refinement. We consider any open cover, and we consider the family of functions provided by the partitions of unity theorem. Of course, the supports of these functions are not necessarily open sets, okay? But the interiors are open sets. And what we get is that the interior of the support of theta I is contained in ui. So it satisfies one of the conditions of a refinement. The other one, of course, it is that it has to be a cover, but that's also true because since the sum of the theta i's is equal to 1, then if we consider a point in M, there exists an index such that the value of x is positive. And in particular, that happens in a neighborhood of x. So what happens is that x is an interior point of the support of theta I sub 0. So any point of M is contained in one of these interiors. So the union of these interiors is M. And so because of that, this is a refinement of the open cover, of the initial open cover. But it is obviously locally finite because the family of the supports of theta I was already locally finite and the interior of the support is contained in the support. So this family over here is an open cover that is a refinement of the initial open cover, and moreover, it is locally finite. Okay, so we got a locally finite refinement for any open cover of our manifold. And so in particular, our manifold is paracompact. Okay, so paracompactness is also a necessary condition in order for the partitions of unity theorem to hold, right? It is difficult to exhibit an example of a non-paracompact manifold. For instance, there is a very famous one which is called the long line or Alexandrov line, but the construction is a little bit tricky. And we are going to see why it is not so easy to find such examples. Consider a manifold M which is connected and Hausdorff. We already saw that Hausdorff is a very natural property because otherwise the partitions of unity theorem does not hold true. So the following properties are equivalent. The first one is that M is paracompact. The second one is that M has a countable base of open sets. It is interesting that this condition has already appeared. It has appeared in the hypothesis of Sard theorem. So this is the second instance in which we have to consider a countable base of open sets. And finally, the third condition is that M can be written in the following form: as a union of compact subsets of M, where every one of these compacts is contained in the following one. It's a union of K sub j, where j runs in the natural numbers, and K sub j is contained in the interior of K sub j plus 1 for every j. Okay? And let's make a couple of remarks. First one is that space with a countable base of open sets is called second countable, and so it is natural to work with these spaces because of this theorem, because of this characterization of paracompactness, and also that this family of open sets, that it is a cover of M such that every compact set is contained in the interior of the following one, is called an exhaustion by compact sets. In this lecture, we introduce the partitions of unity theorem and we discuss its hypothesis. Indeed, there are two necessary conditions for the theorem to hold, namely, the manifold has to be Hausdorff and paracompact. Moreover, these conditions are sufficient to, as we will see in the proof of the theorem in next lecture. Thank you for your attention.